Hello everyone and welcome back to another lecture of electronic measurements and instrumentation. In the previous lecture we discussed about the static and dynamic response of measuring instruments. In today's lecture we are going to study about the electronic meters. So the lecture outline for today is we are going to revise a bit about the basic concepts which we have already discussed probably in previous semesters about the electromechanical meters or electrical meters. Then we will be discussing about why we need electronic meters and what are its advantages. Then we are going to study about the transistor voltmeter circuit with certain mathematical examples based on that, and we will see how we can change the range of an electronic voltmeter. So, to begin with, what are electromechanical meters? Electromechanical meters, like we have already studied in the first lecture, probably where we were discussing about the various classifications of measuring instruments. There we talked about electrical instruments, electronic instruments, so how they are different from each other. Electrical instruments are those, a broad category being an electromechanical instrument, which says where you provide it with an electrical energy and it converts into a mechanical motion of certain parts of the instrument, like the pointer. So the pointer gets deflected and it gets deflected in proportion to the amount of current or voltage you are providing it. So any instrument which is based on that is actually an electromechanical instrument. The most common electromechanical instrument that you might have already studied about is a PMMC instrument. PMMC stands for permanent magnet moving coil instrument, which actually works on motor action. These are also called as d'Arsenal instruments. And why it is called a PMMC instrument? Because the most important two parts of it are a permanent magnet and a moving coil. When a moving coil is put in the magnetic field of a permanent magnet and a current is passed through that thin coil, so what happens is the magnetic field induced in the coil because of the current and the magnetic field of the permanent magnet, they interact with each other and there is a deflection of pointer, and so that is a PMMC instrument. From a PMMC instrument we can measure current, voltage, and so on. So there are different electrical instruments. So that this electrical instrument, this was based on magnetic field. So we can also have electrical instrument based on electromagnetic field of attraction or repulsion. We can have certain analog instruments which are based on the principle of electrostatic effect. Some are based on the induction effect, some are based on heating effect. So we can have different types, like certain electrostatic effects can be used to measure power or in watt meters. Induction effect can be used in energy meters, so on and so forth. So the basic thing is that these are all electrical meters. But now this chapter has to discuss about the electronic meters. So basically electronic meters are a modified version of electrical meters. Electrical instruments plus amplifiers will give you an electronic instrument. So obviously, say what are the disadvantages that we have faced in the analog instrument or electrical instrument? Say let us talk about an electrical voltmeter. There may be certain voltages which are very small. Since any of the electromechanical meter, it works on the motion of certain parts of the instrument. But when, say, the voltage is so small that it produces such a feeble current and such feeble magnetic field that the pointer is hardly able to move or show you the correct reading of that particular quantity. So in that case you say what, its sensitivity is less. So basically the sensitivity of electrical instruments is far less. Also, say we say in a voltmeter, what is the desirable condition is that it should have infinite amount of resistance. Even if it is not infinite, so practically it should be as high as possible. But with electrical instrument, what happens is it has certain amount of resistance, and it is not that high. Or if it is not that high, that means what, it can load your circuit. जैसे अगर से मुझे किसी चीज़ के से या रजिस्टर के अक्रॉस मुझे वोल्टेज मेजर करनी है, लेकिन जो मेरे से वोल्ट मीटर की रेजिस्टेंस है वो उस रेजिस्टेंस से कम है जिसके अक्रॉस मुझे वोल्टेज मेजर करनी है. सो व्हाट हैपेंस इज दैट दैट वोल्ट मीटर विल बाईपास दैट करंट ऑब्वियसली. And because of what will happen is that means your voltmeter is being loaded. Also, जो resistance जिसके across आपको voltage measure करनी थी, उसके अक्रॉस जो है कम करंट फ्लो करेगी, क्योंकि उसकी रेजिस्टेंस ज़्यादा करंट फ्लो करेगी. सो उसके अक्रॉस कम करंट फ्लो करेगी, दैट मीन्स उसके अक्रॉस जो वोल्टेज ड्रॉप भी होगा वो भी कम होगा. सो वी विल नॉट गेट द एग्जैक्ट वैल्यू ऑफ वोल्टेज दैट इज अदरवाइज इन दैट रेजिस्टेंस व्हेन द वोल्ट मीटर वाज नॉट अटैच्ड अक्रॉस इट. सो these two things, these made or forced the scientists to devise another type of devices which are electronic instruments. So these two disadvantages को overcome करने के लिए, what are the two disadvantages? One is about low voltages and second is about low input impedance के लिए. So या फिर इसको हम बोल सकते हैं low sensitivity also. So to increase the sensitivity of the electrical instrument, what we do is हम जो signal हमारे पास आ रही है, if that is very small, we are going to amplify that signal. So when we amplify that signals, then we apply it to the electrical meter. The combination of amplifier plus your electrical instrument gives you an electronic instrument. Why is it called electronic instrument? Because mostly amplifier क्या हो सकता है, either it is your say transistor, it can be a field effect transistor, it can be an IC. Earlier we used to use vacuum tubes, okay, but since vacuum tubes are obsolete now, we are not going to use them. So all of these are actually what, these are electronic things only. So that is why whenever you use these as amplifiers plus you're already having a deflection instrument which can be an electrical instrument, so a combination of these, it will increase the sensitivity of your voltmeter, ammeter or whatever you are using. So this amplification which is being provided to the small signal, it increases the sensitivity. So our first disadvantage of the electrical instrument is removed. Also, we have said that the input impedance of electrical instrument is less, which leads to loading off in case of a voltmeter. Okay, so also another thing is that क्योंकि हमारे पास जो एनालॉग वोल्ट मीटर या इलेक्ट्रिकल वोल्ट मीटर होता है, हम अगर उसकी रेंज चेंज करते हैं, से पहली रेंज उसकी है मिली वोल्ट की, दूसरी है से वोल्ट की, ठीक है. सो से मैं इस रेंज से इस रेंज में स्विच करती हूँ, तो उस केस में भी इनपुट इम्पीडेंस जो है हमारी चेंज हो रही है. इसमें कुछ सर्टन इनपुट इम्पीडेंस होगी और वोल्ट की रेंज में कुछ सर्टन डिफरेंट इनपुट इम्पीडेंस होगी. सो व्हाट इज डिजायरेबल इज also कि हमारी जो है input impedance that should approximately remain the same even if we are switching through different ranges of the voltage measurement. So that is also overcome in इलेक्ट्रॉनिक इंस्ट्रूमेंट्स. हाउ दैट इज़ ओवरकम इन इलेक्ट्रॉनिक इंस्ट्रूमेंट, क्योंकि यूजुअली जो इलेक्ट्रॉनिक इंस्ट्रूमेंट्स है जैसे कि ट्रांजिस्टर है, फील्ड इफेक्ट ट्रांजिस्टर है, ये एम्पलीफिकेशन भी प्रोवाइड करते हैं. ऑल्सो इनकी इनपुट इम्पीडेंस जो है वो बहुत ज़्यादा होती है. इनपुट इम्पीडेंस बहुत ज़्यादा होगी, ये पहले ही हम एक सर्किट के लगाते हैं, पहले एम्पलीफायर लगेगा फिर हमारा जो है इलेक्ट्रिकल इंस्ट्रूमेंट लगेगा, उसकी वजह से हमारे जो पूरे ओवरऑल मीटर की इनपुट इम्पीडेंस जो है वो इंक्रीज हो जाती है. Also, if we are, since वही field effect transistor throughout use हो रहा है circuit में, even if we are changing the range of the circuit, then also its input impedance remains same over different ranges. So our another disadvantage which we were facing with the electrical instrument is also removed when we are using the electronic instrument. सो इलेक्ट्रॉनिक इंस्ट्रूमेंट के तीन बेसिक चीज़ें हैं. इफ़ वी आर, आई एम नॉट जस्ट टॉकिंग नाउ अबाउट द वोल्ट मीटर, आई एम टॉकिंग अबाउट इन जनरल. तो थ्री थिंग्स आर देयर. फर्स्ट thing is transducer. Second important component of an electronic instrument or electronic measuring instrument is signal modifier. And the third important part is indicating instrument. Okay, transducer, as we already know, it converts energy from one form to another form. Okay, this is the first sensing instrument in case of an electronic instrument. It may or may not be there. ट्रांसड्यूसर हम कब यूज़ करते हैं, जब हमारे पास जो क्वांटिटी होगी दैट इज़ नॉन इलेक्ट्रिकल और फिजिकल इन नेचर, जैसे टेम्परेचर हो गया, प्रेशर हो गया. लेकिन ऑलरेडी अगर हमें डायरेक्टली रेजिस्टेंस के अक्रॉस करंट मेजर करनी है या वोल्टेज मेजर करनी है, सो वो ऑलरेडी एक इलेक्ट्रिकल क्वांटिटी है. सो वी डू नॉट नीड ट्रांसड्यूसर इन दैट केस. सो ट्रांसड्यूसर डज व्हाट, इट कन्वर्ट्स एनी ऑफ द physical or non-electrical quantity into an electrical quantity. ठीक है, its function is that only, and it is an optional part. It is used only if the quantity which we are measuring is a non-electrical quantity. Then signal modifier. Signal modifier obviously here in this case is a transistor or a field effect transistor, which does what, amplification. Okay, it's not necessary we can use only these instruments. We can also use, say हमारे पास AC है और हमें उसको DC में कन्वर्ट करना है, सो हम क्या यूज़ कर सकते हैं, रेक्टिफायर्स भी. कोई सिग्नल्स हमें नहीं चाहिए तो हम फिल्टर्स भी यूज़ कर सकते हैं. सो सिग्नल मॉडिफायर्स कैन बी एनीथिंग. दे कैन बी एम्पलीफायर्स, रेक्टिफायर्स, फिल्टर्स, वेव शेपिंग सर्किट्स, एनीथिंग. Okay, so this is another part. Then the third is your indicating instrument, which can be your any indicating instrument, ammeter, voltmeter, ohm meter, चाहे वो PMMC instrument हो, moving iron instrument हो, या फिर electrodynamic meter हो, कोई सा भी चलेगा. Only these things should be kept into mind. So the three important components of any electronic meter is, it's the transducer, then signal modifier, and indicating instrument. So to begin with, three advantages we can think, some advantages that we can think of now of electronic instruments is that it has low signal level detection. इसमें power consumption भी जो है वो कम होती है as compared to your electrical instrument. इसकी frequency range भी जो है that is more than your normal electrical meters. इसकी input capacitance कम होती है और इसमें loading errors भी कम होते हैं. So because of all these advantages, we prefer electronic meters over electrical meters. Okay, so today we are going to discuss about one of the very important electronic meter, which is electronic voltmeter. Electronic voltmeter को हम लिखते हैं EVM, और सबसे important electronic voltmeter है transistor electronic voltmeter. So now one of the most important transistor, or which forms the basis of the electronic voltmeter, is transistor voltmeter, in which we are going to use an emitter follower voltmeter. Emitter follower voltmeter means it is actually a common collector, a transistor which is used in common collector configuration. Why is it called as an emitter follower voltmeter? Because here we are going, whatever we provide at the input, almost same we will get at the output, and output is taken from the emitter here. Okay, so emitter mostly follows whatever is coming at the input. That is why it is called as an emitter follower circuit or voltmeter. So the voltage that we are going to measure, we are going to apply it between the base and emitter, and whatever voltage that we are going to measure, that will come across the emitter. So for obviously, since it is a common collector configuration, input will be base side, output will be emitter side, and collector is common to both input as well as output. So voltage that we are going to measure is E, that we are going to apply between the base and emitter terminal, and output we are going to measure between the emitter terminal. So here and here we are going to measure. That is why we have connected our PMMC or electrical instrument, electrical voltmeter, here between this emitter point and here, which is here. So now the input current is IB here. Okay, current passing through the meter is actually IE, which is equal to IM, which is passing through the meter. So meter के through वही current जा रही है जो emitter के through आ रही है. So here it is like that. Now how do we say that this has done this is an electronic voltmeter? So in this case, how we justify that? VCC is basically जो आप supply voltage provide कर रहे हो between collector and between this emitter side. Voltmeter loading is greatly reduced by using this emitter follower configuration. An emitter follower offers a high input resistance to voltages being measured and provides a very low output resistance to drive the current through the coil of the deflection meter. Okay, the basic emitter follower voltmeter is having this PMMC instrument. The DC supply is connected between the collector and the emitter, where the positive of the VCC is connected to the collector and the negative is connected to the emitter. The voltage to be measured, its positive is connected to the base and its negative is connected to the same terminal where the supply's negative terminal is connected. Now obviously, since this transistor is being used as an amplifier, so there will obviously be amplification of the current. That amplification of the current is provided by जो हमारे पास output current है to the input current. Output current है IE, या फिर हम इस IE को हमने already said, we have said that IE is equal to IM, और input current हमारे पास है IB. So this is the current amplification factor. Say if usually it is represented in terms of beta, but here we are going to represent it in terms of H parameters. So HFE, we are going to take this term as HFE. So the current amplification factor which is being provided here is this value. Also, if I have to find out the input impedance, जो हमारे पास input impedance है यहाँ पे, that input impedance, how are we going to visualize that? जो हमारे पास यहाँ पे voltage है to whatever resistance we are looking at here. So your input impedance will be equal to जो voltage हम यहाँ पे देख रहे हैं divided by, obviously your resistance is, input resistance is actually equal to the ratio of the input voltage, यहाँ पे input voltage E है, to the input current which is IB, and this is always much greater than RS plus RM. RS plus अगर हम डायरेक्टली इस मीटर से मेजर करते हैं वोल्टेज, तो इसकी इनपुट रेजिस्टेंस कितनी होती है, जो हमारे पास सीरियल में कनेक्टेड है सीरीज रेजिस्टर, प्लस जो हमारे पास मीटर का मल्टीप्लायर रेजिस्टेंस है. तो जब हम ट्रांजिस्टर कनेक्ट करते हैं उस केस में हमारी इफेक्टिव इनपुट रेजिस्टेंस है E by IB, and always this resistance is much greater than this resistance. This we will get to know with the help of the example that we are just going to discuss. So the question says that in a simple emitter follower voltmeter circuit which is given above has VCC equals to 20 volts. This voltage is equal to 20 volts. RS plus RM, यानी कि this part, this is equivalent to 9.3 kilo ohms. VCC was given to be equal to 20 volts, and IM is equal to 1 milliamperes at full scale deflection. That is, maximum current that it can measure is 1 milliamps, not more than that, and the transistor current gain is equivalent to 100. What we have to find out is calculate the meter current when E is equal to 10 volts. E is also given to be equals to 10 volts. That means we have to find out the meter current, which is IM or IE. So IM will obviously be equivalent to, meter current will be equal to what is the voltage across this divided by the resistance. voltage across this, यानी कि emitter voltage, whatever is the emitter voltage divided by resistance of this part. Resistance of this part is Rs plus Rm. So emitter voltage this is will be equal to whatever is this voltage, which is this voltage minus whatever is the drop at this junction, which is 0.7. So this is actually VBE. Okay, so VE is actually equal to E minus VBE divided by Rs plus Rm. E is given to be 10 volts minus drop across the base emitter junction is 0.7 volts divided by Rs plus Rm is already given to be equivalent to 9.3 kilo ohms. So that will be equal to 9.3 kilo ohms. So this will be equal to 9.3 volts divided by 9.3 kilo ohms. So that will be equal to 1 milliamperes of current. So Im is equal to 1 milliamperes. Im we already know it is equal to IE also. Okay, so this is the current. This is our first part. Calculate the meter current when E is equal to 10 volts. Next is we have to determine the voltage input resistance, voltmeter input resistance with and without the transistor. Without the transistor we already know it is 9.3 kilo ohms. Okay, with transistor the input resistance is equivalent to Ri. We have already written Ri is equal to E over IB. E we already know it is 10 volts, and IB we have to find out. IB has a relation with this. Okay, IM we already know, HFE we already know, so we can find out IB. So IB will be equal to Im divided by HFE. Im we have already calculated is 1 milliamperes divided by HFE is equal to 100. So that is equal to 10 microamperes. IB will be equal to 10 microamperes. So we'll put this here. Okay, so Ri input resistance with the transistor is 10 volts of E divided by 10 microamperes of this, so that will give you around 1 mega ohm of input resistance. So input resistance with transistor is 1 mega ohms, whereas the input resistance without transistor is Rs plus Rm, which is 9.3 kilo ohms. So this is what I was telling you previously, that Rs plus Rm is always much less than Ri. So Ri is much greater than Rs plus Rm. Obviously this is of the range of mega ohms and this is of the range of kilo ohms. Because of this increase in the input impedance, the loading effect is reduced. Also, since transistor provides the amplification of the current, also its sensitivity is increased. Now there is a disadvantage of this circuit. This is just for actually the basic understanding of the emitter follower voltmeter. Otherwise this is not the practical circuit of emitter voltmeter. Why? What disadvantage does it have? The disadvantage here is that this voltage drop because of this VBE introduces an error of zero point 0.7 volts. How? Like here when we applied the input voltage to be equal to 10 volts, so we had a current here of 1 milliamperes, that means full scale deflection. So we can calibrate this meter from 0 to 1 milliampere, it is the ammeter, and for voltmeter it will be calibrated from 0 to 10 volts. So at center it should be having what value here? When it is 0.5 milliamperes, then only it will show you the 5 volts. Obviously when it is 0.25 milliamperes, so it will show you 2.5 volts, and like that. That is how you calibrate the scale of ammeter in terms of the voltage which is being applied at the input. So this voltmeter, emitter follower voltmeter, should have a range of 0 to 10 volts. Okay, because this ammeter has a range of 0 to 1 milliamperes. Okay, so at this also the scale is going to be linear. सो दैट मीन्स जब मैं यहाँ पे इनपुट वोल्टेज अप्लाई करूँगी 5 वोल्ट्स की, तो ये आउटपुट जो डिफ्लेक्शन मीटर है ये हमें दिखाना चाहिए करंट ऑफ 0.5 मिली एम्पेयर्स, जबकि वो नहीं दिखाएगा. वाई? बिकॉज दिस इंट्रोड्यूसेस एन एरर. दिस विल शो यू अ डिफरेंट वैल्यू. वाई? बिकॉज वी नो आई एम इज इक्वल टू जो हम इनपुट में वोल्टेज देंगे माइनस जो हमारे पास ड्रॉप होगा डिवाइडेड बाय दिस रेजिस्टेंस. इनपुट पे हम इस बारी क्या वोल्टेज यूज़ कर रहे हैं? 5 वोल्ट्स माइनस हमारे पास 0.7 का ड्रॉप हो गया और ये हमारे पास 9.3 है. सो दैट विल गिव यू around 4.3 volts divided by 9.3 kilo ohms, so that is around 0.46 milliamperes. Rather यहाँ पे at input 5 it should give you 5 milliamperes reading, then only it will show you exact of how much? 5 volts. So because of the drop of this voltage across the base emitter terminal, it gives you an error. How this error can be overcome is we can eliminate this error by using a potential divider and an additional emitter follower circuit, whose circuit I'm just going to show you. This is the practical emitter follower circuit, which uses a plus minus or dual polarity supply, plus VCC being plus 12 volts and minus VEE being minus 12 volts. Typically, this is the voltage being applied to the collectors and emitters of the two transistors. Transistor Q1 has a base which is grounded, and that means its base is connected through a resistance R1 to ground, and there is a potential divider provided by resistors R4, R5 and R6, which provide an adjustable bias voltage to the base Q2, which is VP. So that means input voltage E, which we have to measure, is connected to the base of transistor Q1, and this potential dividers provides voltage VP, which is also grounded, okay, through this. That means VP should mostly, we should, in order to keep the bias correct, we should always connect it to ground, or the voltage across this should always be equal to 0. Resistors R2 and R3 connect the transistor emitter terminals to the negative supply voltage minus VEE or minus 12 volts, as we have discussed, and the meter circuit is connected between the two emitters of the transistors. The circuit input resistance is whatever resistance we can look from through here. Okay, so that is whatever is the resistance that in parallel with R1, that is the total resistance of this voltmeter circuit. Now, when no input voltage is applied to this voltmeter, that means this E is equal to 0, the base voltage of this transistor Q1 is adjusted to give a this meter, which say here is a M meter with maximum deflection of, say again, 1 milliamperes. That means it should be such that when this is equal to 0, the meter should be showing the reading obviously equal to 0. Then only we can say there is a 0 voltage. How we can achieve that is, when here we have a 0, we are going to adjust this voltage divider in such a way that this VP is equivalent to this voltage, and this will be equal to 0. This voltmeter is actually doing what? This is giving you difference between these two voltages. If current flowing from this part and current flowing from this part is same and opposite, they will, this minus this will give you actually 0 reading. So that is how it is done. So we make this V, when this is equal to 0, we make this VP equal to 0, which will give you the voltage across this voltmeter 0. This voltage is difference from this point. Say I write this voltage to be equal to, since it is of emitter 1, so VE1, and this is of emitter second of the transistor Q2, so I will write this voltage to be equal to VE2. So this voltmeter measures the voltage, say V, and that V is equal to VE1 minus VE2. सो VE1 इज इक्वल टू हाउ मच, जितनी वोल्टेज हम यहाँ से अप्लाई कर रहे हैं माइनस दिस वोल्टेज से 0 माइनस 0.7, सो दैट इज इक्वल टू 0 माइनस 0.7 माइनस यहाँ से हमने इसको वोल्टेज कितनी सेट की है VP को, अगेन 0 माइनस इसके अक्रॉस जो ड्रॉप है वो दैट इज इक्वल टू 0.7, सो दैट विल गिव यू माइनस 0.7 प्लस 0.7 इक्वल टू 0 वोल्ट्स, या फिर करंट भी इसके थ्रू 0 होगी, सो दिस विल गिव यू अ 0 रीडिंग, सो इट विल मेजर अ वोल्टेज ऑफ 0. This is how we do it or calibrate it in the beginning. Now say if E is equal to 5 volts, now we have already, now we don't have to touch with this part of the circuit, we have already connected it for when earlier this voltage was 0, we have already put this or adjusted this voltage divider circuit and made this VP equal to 0. Now we do not need to change this part of the circuit. Now say E, this was the case when E was equal to 0. Now this was say case first. Now we have case second where say E is equal to 5 volts. When E is equal to 5 volts is applied here, again we need to measure the voltage V. V is again equal to VE1 minus VE2. In this case now VE1 is equal to how much? 5 volts being applied here minus 0.7 volts of drop across this base emitter terminal, so that will be equal to 5 minus 0.7 volts minus VE2 is VP minus, this is equal to E minus VBE1 minus, this is VP minus VBE2. Okay, so VP is already set to 0 minus 0.7, so it will give you 5 minus 0.7 minus 0.7 minus 0 plus 0.7, so this will cancel each other out, so we will have 5 volts. So the voltage drop which happens here in the previous circuit, since we used only this part of the circuit, because since we used only one transistor, so that error was introduced because of this drop of 0.7 volts. But now since we are using two transistors connected opposite to each other, that means अगर यहाँ पे plus 0.5 volts का drop हो रहा है, यहाँ पे minus 0, या फिर हमें क्योंकि difference लेनी है, these two voltages will cancel each other's effect out, या फिर this error will compensate for this error, and we in the end our error is actually corrected and we will have the correct value of the reading. So in this case this is actually the practical circuit where there is no error introduced or error cancels each other. Errors in the two transistor or drops in the two transistor will cancel out each other's effect. Next question based on the above circuit is that when an emitter follower voltmeter or circuit like the above has R2 equal to R3 is equal to 3.9 kilo ohms, that means R2 is given to be equal to 3.9 kilo ohms, also R3 is given to be equal to 3.9 kilo ohms, also VCC is given to be plus 12 volts and minus VEE is minus 12 volts. Determine I2 and I3 when E is equal to 0. Initially I is equal to 0. This is case first when E is equal to 0. In that case what is the current? I2 and I3. I2 is the current flowing through resistor R2 and I3 is the current flowing through resistor R3. Now first part we have to find out I2 and I3 when E is equal to 0. Second we have to calculate the meter circuit voltage, that means voltage V when E is equal to 1 volts and E is equal to 0.5 volts. How are we going to proceed with this now? So in the A part we have to find out I2 and I3. I2 is the current passing through this portion. Current passing through this will obviously be equivalent to whatever the voltage is there, that means whatever is the voltage across R2, or I can call it say VR2 divided by whatever is the resistance R2. So I can write here is I2 will be equal to voltage across this, that means VR2 divided by whatever is the resistance R2, and I3 will be equal to VR3 divided by R3. Since R2 and R3 are both equal, also here, since voltage here is 0, Vp is voltage E is equal to 0, Vp we have also put equal to 0. When these two voltages are 0, voltage drops here are equal, that means here voltages will be equal also, that means Vr2 will be equal to Vr3. Already R2 is equal to R3, that means currents I2 will also be equal to I3. Whatever the value you get, you can find them separately, or even if you find out the value for one, the same will be applicable to another one also. Now Vr2 is equal to, we have to find out Vr2 is equal to, how much is Vr2? Vr2 is this voltage. This voltage is equal to this voltage minus this voltage minus this voltage will be this value. यानी कि इन दोनों की value minus this value will be this value basically. So Vr2 will be equal to E, which is 0 volts, minus VBE1, whatever is the drop at base emitter junction of transistor 1, minus whatever is the value of negative supply of the voltage, which is minus VEE. So that will be equal to Vr2. Since E is equal to 0, this value is minus 0.7 volts. This is minus 12 volts. So that will be equal to actually 11.3 volts. The same will be for Vr3. So Vr2 equals to Vr3 is equal to 11.3 volts. Now I2 is equal to 11.3 divided by its value of R3 is 3.9 kilo ohms. So the value will be approximately equal to 2.9 milliamperes. So if I2 is equal to 2.9 milliamperes, so that means I3 will also be equal to 2.9 milliamperes only. Okay, so with this we have solved the first part where we have determined current I2 and I3 when E was equal to be 0. Now we have to calculate the meter voltage when E is equal to 1 and when E is equal to 0.5 volts. So B part of this circuit will first say V of I is when E is equal to 1 volts. When V is equal to 1 volts, we have to find out the value of voltage across the meter circuit, which is equal to V. V is equal to VE1 minus VE2. VE1 is equal to how much? We've already done E minus VBE1, and this VE2 is equal to VP minus VBE2. Okay, so E we have already given is 1 volts minus BE1 is 0.7 volts minus Vp is 0 volts minus VBE2 is 0.7 volts. So this is equal to 0.3 volts minus 0 minus 0.7 gives plus 0.7. So that will give you 1 volt of reading. The same procedure you will get for second equation and you will follow, and when input you put equal to 0.5 volts, you should also have the input to be equal to the output of from the meter reading of 0.5 volts. This you will do on your own. Okay, so this was about how we find out the voltages using electronic voltmeters. Now in the next lecture we are going to discuss about the voltmeter range changing. This is it for today. Thank you so much.